Welcome student, PCH 280151 unit for reaction mechanism, in which we are going to discuss today, that is ET reaction, electron transfer reaction. I am Dr. Devangar Pandya from Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. Point to discuss in today's lecture in ET reaction. We're going to begin this lecture by introduction to redox reactions or electron transfer reaction. We're going to define it and learn the different type of this ET reaction in ligand substitution reaction of transition metal complexes. Redox reaction in transition metal complexes with certain illustrations. We're going to discuss how the redox reaction proceed in transition metal complexes ligand substitution reaction. Type of redox reactions in which outer sphere or inner sphere reaction mechanism would be there. So we're going to discuss the type of redox reaction in this unit. Let's begin with the introduction to redox reactions or electron transfer reaction, how it is defined. The redox reactions are basically electron transfer reactions, can be chemically defined as it is the study and manipulation of valence electrons of atoms or molecules. So here the valence electron which remain in atom or molecule, that will going to transfer, and there should be certain other rules regulation apply in this reaction, because this is not simple redox reaction like metal will lose electron and non-metal will gain electron and that kind of thing. Here there are certain conditions which will facilitate this kind of electron transfer reaction in complex transition metal complexes. As far as the principle of this redox reaction is concerned, the principal redox reactions are considered as electron transfer reactions, which is abbreviated as ET reactions. However, mechanistic studies have demonstrated that in some of the redox reaction, transfer of atoms or ions take place. So the electron will be transferred from one species to other, but along with that, in certain cases here we can see some atoms or ions can be transferred as well, and on the base of that we can count the redox reactions. Redox reactions need straightforward transfer of electrons, and when straightforward transfer of electron is concerned, we have certain points for that. Electron transfer take place from one metal to another metal in electrochemical cell. That is the first you can see in the redox reaction. And second, transfer of group of ligands along with their electrons that can efficiently oxidize or reduce a metal center. So two type we can include over here. One is direct electron transfer from one metal to other, electrochemical cell would be there, or either a group of ligand or single ligand may transfer from one complex to other, and as a result of this ligand transfer, their electrons transfer would be there as well, and it can effectively oxidize or reduce the metal center of the complex compound. Now, prior to define the concept, one must understand the meaning of oxidation and reduction. There should be 6 different definitions associated with these two terms, oxidation and reduction. Electron transfer, gain of electron, loss of electron, increase of oxidation state, decrease of oxidation state, substitution of electropositive element, addition of electropositive element, substitution of electronegative element, addition of electronegative element. So these are so many definitions associated with this oxidation reduction, and redox reaction literally visualize the transfer of this species between two redox partners. So to make it visible or visualize, We can even use some radioactive element to substitute one element from other and can make impact on the central metal ion, losing or gaining the electron, getting or going to be oxidized or reduced, and that way we're going to witness or notice a redox reaction, especially in complex compounds. First point, the electron or either electrons may be transferred, hydrogen atom or hydride ion would be there, oxygen atom would be there which is electro-rich, chlorine atom would be there which is electro-rich. So these are certain other points which you may include in the redox reactions. In general, we consider redox reactions as electron transfer which take place from one species to other species. Here is a simple common reaction has been given. A will lose gain the electron, B will lose the electron, and that way A, after the reaction, A turns neutral to electronegative, and B, which is electronegative, turns to neutral. And that is how electron transfer take place, which result into oxidation reduction reaction simultaneously, known as redox reaction. In a redox reaction, oxidation and reduction both occur simultaneously, which already I have said. Nevertheless, we have to define both oxidation and reduction separately. So half reaction in the redox is oxidation reaction and half other is the reduction reaction, sorry. It is possible by numerous ways to define word oxidation, although the most prominent definition includes oxygen addition, hydrogen removal, transfer of electron. And additionally, I have already included three more definition: increase in oxidation state, addition of electropositive or removal of electropositive element, addition of electronegative, removal of electronegative element. So there are so many definitions, but among them these are the three main chief. So the mechanism of a redox reaction can be understood if one clearly finds out whether the transfer of an atom, a group, or an electron has occurred during the course of reaction. In addition, it is necessary to know which atom or atoms is or are transferred, or how many electrons are transferred, along with a kind of transition states of all the steps. An oxidant accepts one electron. It is considered equivalent to the acceptance of a hydrogen atom. And if an oxidant accepts a couple of electrons, it is considered equivalent to accept to a hydride ion. The thermodynamic features of the redox reactions are of basic importance, but above mentioned information can be obtained by kinetic measurements. So kinetic measurements gives information regarding the oxidant will accept a single electron or a couple of electrons, or it may be we can consider it as equivalent to hydrogen atom or equivalent to hydride ion. The important information on the mechanism of an electron transfer reactions will be obtained by methodical kinetic studies of the reduction of cobalt-3 complexes in the organic solvent and in organic solvent water mixture. These studies were carried out because the complexes of cobalt in the oxidized form, that is cobalt plus 3 oxidation state, are inert kinetically, whereas labile in the reduction form, that is in CO plus 2. And this combination is required for this electron transfer reaction. Metal center should remain similar, only electron transfer from one metal to other take place. Likewise, the kinetic study of chromium plus 3 to chromium plus 2, that is pi d3 to pi d3 sigma d1, Couple in an octahedral system can be investigated because the sigma electron in chromium 2 is antibonding in nature, which is accountable to the tetragonal distortion in chromium 2 complexes, whereas their vast labile character relative to those of chromium 3 complexes, and we have discussed this geometrical disturbance, or we can say vibronic coupling, in the semester 6 in depth. So I'm not going to include that much here, but why this chromium 2 is got labile compared to chromium 3, or cobalt 2 is more labile compared to cobalt 3, which already we have discussed the lability and inertness in semester 6, the kinetic parameter of these metal centers. It should be noted that Ru3 to Ru2 ruthenium pi d5 to pi d6 redox couples in a low spin octahedral complexes exhibit quite opposite behavior, since ruthenium 2 system in this case is inert in comparison with the +3 oxidation state. So opposite behavior we witness over here compared to chromium and cobalt. So that means electronic configuration have any different role in this electron transfer or ET reaction, we can say that. Here it is noteworthy to mention that in contrast to the electrochemical reactions involve charge transfer heterogeneously, in a homogeneous reaction both the donor and acceptor are in the same phase, that is in a solution phase, and therefore mechanism basically involves the concerned participating species in the solution. Now redox reaction in transition metal complexes. Redox reactions are, we can say, electron transfer reaction, abbreviated as ET reactions of metal complexes, are one of the fundamental study subjects in inorganic and bioinorganic chemistry, because this will going to facilitate many important biochemical reaction in living bodies like human, animals, plants, etc. Reaction between two metal complexes leading to the change in complementary oxidation state and localized on the metal centers have been investigated and studied comprehensively. Henry Tobey observed that transfer of atom from one metal to another usually needs entrance of first metal, the coordination sphere of second metal ion, from first metal elements and its coordinating sphere. The element or one atom need to transfer to the second metal center's coordinating sphere through either a bridging ligand or by ligand substitution. So two ways are there. The atom will transfer through a bridging ligand, or electron should transfer through a bridging ligand or through ligand substitution reaction. Conversely, some electron transfer can also be resulted keeping the primary coordination sphere of any reactant unchanged, because the electrons can cross the barriers like ligands. Under two main headings, a total of 4 sets of redox reactions are recognized, and that makes the different type of ET reactions. First is outer sphere electron transfer reaction. The sphere word indicates the coordinating sphere in which ligand has coordinating covalent bond with the metal center. That is a secondary valency as far as Werner theory is concerned. So outer sphere electron transfer, which is also known as direct electron transfer, DET reaction, or OS ET reaction. OS, that is outer sphere electron transfer reaction, DET, that is direct electron transfer. So there is no media through which electron transfer takes place. There is no need of bridging ligand over here. And the second one is inner sphere electron transfer. So in inner sphere we can transfer an atom or a group of ligands or ion we can transfer from one coordinating sphere to other, but it should be bounded through bridge from one metal center to other. So through bridging ligand that transfer will take place, that is known as inner sphere ET reaction, ISET reaction, or indirect electron transfer reaction mechanism. So first one is inorganic oxidant and inorganic substrate we require. Second, inorganic oxidant or organic substrate we required. Third, organic oxidant and organic substrate. And fourth, organic oxidant and inorganic substrate. So these are the four classification, and that include into this both kind, outer sphere and inner sphere electron transfer mechanism. The redox reaction concerning metal ions can be categorized on the basis of species transfer, where the electron transfer incorporates ionic sphere or it involves coordination sphere on the metal complex. An example of metal complex based redox reaction we can found over here, where MnO4- manganite MnO4-2. Here metal manganese colored pink and red, so you can understand the oxidation state varies in manganese, and manganese, as you know, is a versatile element in the entire periodic table, having oxidation state from +2 to +7, variable oxidation state available. So it's a beautiful example to start with. A manganate will transfer from one form to other, from -1 to -2, and hence we can found the redox reaction take place over here. The example you can see here, BaMnO4, the precipitate is going to be obtained for phenyl arsenic manganate MnO4, that PPT is obtained for this too. So that should be taken as example for the redox reaction. If the redox reaction involves ionic sphere only, it is considered as electron direct transfer ET reaction mechanism, where the transfer of electron takes place between two species without changing any other parameters. There is no parameter change, only electron transfer from one species to other. While the species are metal complexes, such the type of reactions are called outer sphere reaction mechanism. So this is applicable for metal complexes. When this kind of transfer take place from one sphere to other, one complex to other, then it is considered as outer sphere without changing any parameter. There is no bridging ligand, there is no variation in one complex to other, only electron transfer from one species to other. The characteristic features of outer sphere reactions are: these reactions exclude any bridging of ligands, which already I have said there is no kind of modification between the two complexes, and there is no media between these two complexes as well. So there is no any kind of bridging ligands between two complexes acting as a redox couple. The metal complex redox couples simply function as electron donor, that is oxidation, and electron acceptor, that is reduction system. Here is the common example given. M stands for metal, metal 1 and metal 2 ligand, and charge would be x minus to y minus, and N should be number 1, 2, 3, 4, any you can take. And here you can see from metal 1 to metal 2 electron transfer take place, or metal 2 to metal 1 electron transfer take place, and that result into outer sphere electron redox reaction or ET reaction. The outer sphere mechanism has a special attention, being quite we can say being quite important due to the profound similarity of electron transfer in metal complexes with the electron transfer process is metalloenzyme. So metalloenzyme in which this kind of outer sphere mechanism is going to be observed. So that is why there is a special attention for this, because you can understand what important role metal enzyme play in human body. Zinc containing enzyme or magnesium containing enzymes, these are more important metal enzymes which play a very vital or crucial role in our living system or biological process. Theoretically, transfer of electron occurs from reductant to oxidant without causing any modification in the coordinating spheres. That means there is no change in the spectral ligands which already present into the coordinating sphere of the metal, and therefore there is no modification in the coordinating sphere of each redox couple in the outer sphere mechanism. Only the electron transfer from one metal center to other. Such redox reactions are very fast despite electron transfer take place between two substitution inert complexes. So there are certain conditions for outer sphere mechanism as well. We are going to discuss the outer sphere mechanism in depth, but here there is introductory part. I could say that the electron transfer is more, that means the velocity of electron is larger than the ligand's velocity, and both the complexes which involves in this kind of outer sphere ET reaction mechanism should be inert enough so that the ligand substitution take place before that electron transfer can take place. Here is the example for that. You can see iron cyanide complex and octahedral geometry would be there, and iridium chloride complexes would be there as well. Now in both these cases, the cyanide is strongly associated with iron and chloride is little moderately associated with iridium. So before the cyanide or chloride may substitute each other, before that the electron transfer would be there. So Frankel-Coden principle can be applied to this Frank-Coden principle, and according to that the velocity of electron is greater than that of nucleus, and hence we are going to found the electron transfer over here. It is an evident for the above reaction that except electron transfer from iron hexacyano complex to iridium hexachloro complex, none of the other parameter get changed. So only the change in the charge you can see over here, -4 which reduced to -3 and -2 which increased to -3. So from -4, one electron from Fe enter into iridium. So oxidation state of Fe get increased from +2 to +3, ferrous to ferric, and iridium will oxidation state get decreased. Here you can see it is -2, and 4 chloride would be there, so +4, it is reduced to +3. So that way we're going to get the outer sphere electron transfer mechanism in this example. There are so many other examples. It is not rigid. We are not that much rigid. You can use only this example. There are so many examples in different reference book. You can use so many different examples for that as well. On the other hand, if the redox reaction includes coordination sphere, now the outer sphere may change with the inner sphere. So if it includes coordination sphere, it is considered as an atom, group or ion transfer reaction where the transfer of atom, group or ion take place between two redox couple, and for that it requires some media where you can use bridging ligand. So while the species metal complexes, such type of reactions are called inner sphere reaction, and in inner sphere reaction, and the reaction couple, whatever complexes are there, their outer coordinating sphere, that means ligand, has get some changes which is not observed in outer sphere. Now it can be observed into inner sphere mechanism. The characteristic features of inner sphere reactions are these reactions require the formation of bridged bimetallic complex in the transition state or intermediate position. So when ligand substitution reaction take place, or electron transfer or ion transfer or group of atom ligand transfer or group of ion transfer take place in the between the redox couple, there should be a breeze between these two metal center. Bimetallic complex is going to be obtained in a transition state, and after the change of one group from one part to other, then the breeze will dissociate and will going to get two different species. That is inner sphere mechanism. And second, in these reactions, ligand transfer take place at the same time with the electron. Ligand transfer also take place simultaneously, which already I have discussed. Here is the common example for that: metal ligand 1, metal 1 with ligand, metal 2 with ligand, and here X is indicated over here, and that X act as a bridging ligand. So in the transition state, this X will going to bound metal 1 and metal 2. Bimetallic complex is going to be observed in this transition state, and then ligand L depart and will going to get the modification in this 2. You can see here M1L, here M1L with X. So the ligand X, bridging ligand, transfer from one complex to other. So coordinating sphere get changed in this reaction, unlike outer sphere. In outer sphere there is no change in the coordinating sphere, outer sphere. Here you can see noticeable change in the outer sphere, and the X will be any anionic ligand. Mostly chloride act as bridging ligand, thiocyanide act as bridging ligand, and we can use so many other ligands as well. So this is a common reaction for inner sphere. And in transition state, bicentric bridging ligand should always been there in this inner sphere. So here this, when these two complex react and it form a bridging ligand, now this is entire going to be a single inner sphere, and therefore it is considered as inner sphere ET reaction. As depicted above, the inner sphere mechanism involves sharing of the ligand between reductant and oxidant in their inner coordination sphere, and the transfer of electron take place across the bridging group. According to electrochemical and structural studies, the redox stability or reactivity of transition metal complexes may be determined by the position of ligand in the coordination sphere pertaining to the redox orbital symmetry, along with the electronic nature of ligands. So symmetry should retain, and this kind of conditions would be there for the inner sphere reaction mechanism. These are other example. You can see here chlorine act as a bridging ligand between cobalt and chloride metal center. So here cobalt and chromium metal center, sorry, between that chlorine act as a bridging ligand. Chromium has aqua ligand 1 2 3 4 5, so sixth ligand is got substituted, and ammonia 1 2 3 4 5 would be there, and this one is a bridging ligand. Now after the reaction, you can see here cobalt, which is carrying pentaamine chloride coordinating sphere, converted to hexa aqua coordinating sphere, and this one chromium has hexa aqua coordinating sphere changed to penta aqua with 1 chloro. That means that chlorine, which is there as a bridging ligand with cobalt, now changed with chromium, and we're going to get this noticeable change in the coordinating sphere. But in a transition state, this is a common coordinating sphere of bicentric bridging ligand intermediate, and that is why the electron transfer or group of atom or ligand transfer take place through this. Electron transfer take place through this, and then we're going to found a noticeable change in the coordinating sphere of these two complexes. It is considered as the electron change from cobalt to chromium or chromium to cobalt through this breeze, and hence it is known as inner sphere ET reaction mechanism. Not that the transfer of electron will result in the change in the total optical rotation, and therefore rate of Rasmussen will be equal to the rate of electron transfer, provided reagent used are taken in equal concentrations. While the metal ion being chromium plus 2, it acts as a reducing agent and favors the inner sphere reaction. The brazing chloride moves towards chromium 2 to chromium 3 by lowering the energy of its acceptor orbital and simultaneously raising the energy of chromium 2 donor orbital. However, much and nuclear motions such as correlation phenomena for ET transfer, electron transfer, are lacking for outer sphere mechanism. Type of redox reaction: one equivalent reaction. There are simple one electron transfer in this reaction. It includes one electron transfer reaction which act as models to understand the process involved in a similar reaction containing more complicated species. The key features for this is electron donor and electron acceptor. Sites of those complicated systems are correlated with simple one-to-one equivalent redox reactions to follow mechanistic pathways. Here the example: cerium plus 3 to cerium plus 4. That means it will gain lose the electron, so the oxidation state increase from plus 3 to plus 4, and cobalt plus 3, which gain the electron and change to plus 2. So that way oxidation reduction take place simultaneously. Here Fe and cobalt has the same kind of reaction involves in this. The kinetic data of oxidation reduction of metal ion can be obtained from the appearance or disappearance of the metal plus charge in the absorption spectrum. In the first reaction, cobalt plus 3 disappears from the solution, which is evident from the absence of absorbance maxima at 605. So during the reaction, you may observe this noticeable change using the absorption spectrum. It strongly supports the reduction of cobalt plus 3 to cobalt plus 2. Likewise, kinetic data of oxidation of iron plus 2 in perchloric acid by cobalt plus 3 can be acquired by making the concentration of both the reactants equal. Second type is 2, that means one equivalent reactions. It is the kind of reaction involves reactants in 2:1 stoichiometry, and several such reactions are recognized. For instance, a reaction of Fe plus 2, 1 equivalent, with oxidant, that is 2 equivalent, from complex wherein either Fe plus 2 or oxidants undergo in unstable state. The reaction is like this one: plus 3 it's converted into plus 2 and plus 2 converted into plus 3. Ferrous to ferric. Here ferric will retain and thulium will even reduce to plus 1. So this is the example of these two one equivalent reactions. The above reactions couple incorporate two consecutive one electron transfer where oxidation takes place at Fe plus 2, whereas reaction at Tl plus 2 in perchloric acid aqueous. Another redox couple, that is between vanadium and Tl plus 3 for oxidation of vanadium plus 4 by Tl plus 3, exhibit analogous reaction mechanism to that of Fe2 and Tl plus 2 shows above. Moreover, following reaction mechanism involves oxidation of this element by cerium in 6.2 molar HNO3 at 54 degrees centigrade. These are certain examples for that. Now two equivalent reactions. These reactions involves both the reactants in two equivalents. However, the equivalence is considered not in moles but the transfer of electron between the reacting species. A fascinating example is depicted over here. Uranium to Tl plus 3. The mechanism of this reaction is shown over here. Complementary redox reactions is other type. If the oxidants and reductions both alter their oxidation state by equal in number, such reactions are called complementary redox reaction. These reactions are important because only one molecule of each reactant is needed to react. For instance, we have stannous plus 2 and TL plus 3. Plus 2 is converted into plus 4 in a pair effect, and this Sn plus 2 converted into Sn4 with this mercury 2. So that 2 electron or 2 equivalent or complementary redox reaction, it is the class of non-complementary redox reaction. Third part, unlike to the complementary reactions when oxidants and reactants alter their oxidation number by unequal, such reactions are known as non-complementary reactions. Therefore, the number of molecules of the reacting species may be different with respect to each other. An example of such reaction we can see over here: Fe plus 3 to Fe plus 2 and Sn plus 2 gives Sn plus 4. Let's sum up this. The basic definition and the concept of redox we have discussed in the first part. It has also been described that such which species are basically transferred that changes the oxidation number of the molecule. How the metal ion come into picture to play as a redox couples has been discussed in this lecture as well. The direct electron transfer from one species to other, which is also known as outer sphere reactions, and it has been explained in this lecture. General scheme of the direct electron transfer process without changing other parameters has been depicted as well. On the other hand, the transfer of a group or ion or species between two redox counterparts, that is also called inner sphere reaction mechanism, has been discussed with schematic representation of bridging of two ligand formation in the intermediate step felicitate electron transfer process. Eventually, types of redox reactions with their salient features have been illustrated. Well, this is enough from my side. Thank you for paying attention to this video lecture. Keep asking questions. As you know, asking questions is a beautiful way to gain knowledge. Thank you.